In today's lesson video, we're going to look at day 7.3, and we are still talking about surface area, but this time we're going to introduce you to some new three-dimensional solids. Last lesson, 7.2, we talked about prisms and cylinders. Okay. Today we're talking about pyramids, cones, and spheres. So first, let's look at what a pyramid is. All right. A pyramid is a 3D solid or three-dimensional solid having length, width, and height with one base. Okay, it can be any shape of the base. All right, any shape could be the base. Now, a lot of times it will appear on the bottom, but it doesn't have to be. What I want you to know about the base, though, is since this is a pyramid, the sides are all triangular faces. Any side of a three-dimensional solid is called a face. So the triangular faces are all on the sides. So any face that is not a triangle has to be the base. Okay, you can write that down if you want. Any face that is not a triangle must be the base. Okay? So to find the surface area of pyramids, it's really just adding up the individual areas again. The base area is going to be the area of that either non-triangular side or bottom side if they're all triangles. And then the triangle area is individually added up. Now, a lot of times those triangles are the same as each other, or maybe opposite sides are the same as each other. So we can kind of take some shortcuts by multiplying by 2, or if they're all the same, multiply by how many there are. But one thing that is important to recognize about this is we're using something called L, which stands for the slanted height of those triangles. The slant height, L, will be the height of the triangle faces. Okay, these triangles along the side. All right, we're slanting that height measurement of those triangles back in. That is not the height of the pyramid, not H. Okay, and one thing that's going to be useful from time to time is also recognizing this, that if I use this slanted height L and the height of the pyramid back to the middle of that base, and I connect them along the bottom, that is a right triangle that goes down inside the pyramid. And again, in right triangles, we might need to use a squared plus b squared equals c squared to potentially find L. L is going to be that hypotenuse of that right triangle that I've just drawn. So we might need to use that. Okay? Well, if I have a pyramid where the base is not a polygon, but the base is a circle, it's not called a pyramid anymore. It's called a cone. Okay? Cone is a 3D pyramid with a circular base. All right? It's a specific kind of pyramid with a circular base. And again, it's just the area of that base shape, which in this case would be a circle, which is where we get this part of our formula. And then this curved surface along the outside that wraps around that cone shape. Think of like a paper cone cup you might have gotten a drink of water with at some point. Okay, when you open that up, it creates kind of a weird part of a circle shape, and that is where this part comes from. Okay, just pi r L. L is still what we call the slant height. And again, you can kind of see this right triangle take shape inside that cone, where we could use Pythagorean theorem, where one leg of the right triangle is the radius of the circle, the other leg is the height of the cone, and to find slant height, that would be our C, our hypotenuse of the right triangle. Okay, so we might use Pythagorean theorem there too. Okay, so to finish out this part about cones, pi r squared represents the circular base or the circle base area, and the pi r L represents the sides of the cone. All right, so that formula is very, very important. Pi r squared plus pi r L. Very similar to the surface area of a cylinder equation, but you'll notice I don't have the big 2's in front of each of those, okay? That's because this is really like half of a cylinder, Okay, we only have one base instead of two. These slanted sides end up taking half of the rectangular side, and so it works out very much like that formula, but it's just half. And then we have two new figures we want to talk about, really just one, but there are two separate formulas to figure out, and that's a sphere. Okay, you guys know what a sphere looks like. A globe is a sphere, any kind of round ball like basketball, baseball, those are all spheres, all right? It's a three-dimensional solid in which each point is equidistant. All right, that's a big word. Equidistant from a center point. That means any point on the sphere out here, anywhere, is going to be the same distance from that center, no matter where I put that. Okay? So equidistant means same distance from the center point. And the distance from that point to any point on the circle is still called the radius. Okay? So this formula is very, very simple. For a sphere, the surface area of spheres is the formula 4 times pi r squared. It's like saying we could wrap 4 circles with a radius of r around that, and it would fill in that surface area completely if we could cut them apart and take little pieces where they don't overlap. Okay? Now, a hemisphere is like a semicircle. A hemisphere is half of a sphere. Okay? Half of a sphere. We still have a radius r. Now, because it's half of a sphere, I could just take my area of a sphere, 4 pi r squared, and divide by 2. However, if I just cut that open, okay, that does not include this circle on top, but a hemisphere does include that circle. So not only are we cutting a hemisphere in half, we have to also do the area of that circle where we've cut. So the area of a circle, same radius, is just pi r squared. Well, this all simplifies down to this formula, and I'll tell you why. 4 pi r squared divided by 2, we can divide 4 by 2 and get 2. So that's 2 pi r squared plus another 1 pi r squared. These are like terms, so I just combine 2 plus 1, and I get 3 pi r squared. Half of a sphere is 3 pi r squared. A full sphere is 4 pi r squared. Okay? Now let's put this into practice and do some examples. All right? In this example, the first thing we want to do is classify the following shape as either a cone or a pyramid and include the base shape, okay? Or a sphere. So when we look at this, obviously this is not a cone or a sphere, there's no circles. Guys, that's one thing you can do to kind of help yourself out if you're really struggling with how to classify. If there's no circles, it cannot be a cone, sphere, or cylinder, okay? Those all start with either a C or the S, okay? They have circles in them. So this would be a pyramid. Okay, I'm kind of jumping around, sorry. This is a pyramid. But we also want to include the base shape. The base of this pyramid is this side that is not a triangle, okay? This side on the bottom here is not a triangle. That is a rectangle, so this is called a rectangular pyramid. Okay, a rectangular pyramid. So let's go ahead and find the surface area of this rectangular pyramid. Again, like last time, we just want to break it into its individual parts. Okay, well, the base area part, you can even label it as base, okay, or write that it is a rectangle, is length times width, right? Length times width, which would be 9 times 4. So that is 36 square kilometers. But we also want to add in all of the triangle faces, okay? All of the triangle faces. So that's the area of a triangle is base times height divided by 2, right? Well, we have 2 different triangles, okay? We have a triangle that has a base of 9 on the front and back here, so there's 2 of those. Okay, base is 9, and the height of those triangles is 7.3. That's like our L. 7.3 all over 2. But I also have these other 2 triangles on the left and right. This skinnier triangle on the right, again, there's one matching it over here on the left, has a base of 4 times a height of 8.3, or the slant height of 8.3. Okay, so I want you to pay attention to some number tricks. And somebody pointed this out to me in class the other day. He said, Mr. Allred, since I'm dividing by 2 here, but I'm doubling it because there's 2 of them, do I even have to do that part? Right, you could notice the 2's cancel out here, all right? Or stick with just multiplying by 2 after you divide by 2. Okay, if it makes sense to do that, that's fine. Or you can look at this and cancel it, realizing I'm just doing 9 times 7.3 there. When I do 9 times 7.3, divided by 2, then times 2, that ends up being 65.7. And then for the other 2 triangles, the skinnier ones, okay, those 2 add up to a total area of 33.2. Okay, and that comes from that. The 65.7 comes from that. So we're going to add these together now. This will go a little quicker once you get more practice at doing this. When I add these 3 main chunks, I get a total surface area of 134.9. And so to fill in my blank here for my SA surface area, it's 134.9 square kilometers. Okay, let's try and move on to the next one. All right, we want to classify first. Obviously, this should be recognized as a cone. We don't have to specify anything other than just the word cone on that. Okay, the cone has a radius of 9. You need to recognize that's the radius. And this slanted measurement along the outside is called the slant height, L. All right, and we need to really understand slant height for that. Because for cones, our surface area formula is very specific. It is pi r squared for that circular base plus pi times r times that slanted height of 20.1 for that outside surface. So then we fill in. We do pi times 9 squared plus pi times 9 times that 20.1. And then we start to simplify. I could do all of these as decimals. I could try and plug it all in the calculator. It really is helpful to write your work down on paper without getting decimal answers first, meaning leave it all in terms of pi first. 9 squared is 81, so I have 81 times pi. And then 9 times 20.1 is 180.9 times pi. And so I can actually combine those because they're really like terms. They're both in terms of pi. It's like I'm going to undistribute a pi from both of them and just add the numbers 81 and 180.9, which gives me 261.9 pi. Okay, now when I multiply 261 times pi, I get a final surface area of 822.8 square feet for the surface area of that cone. Okay, moving on to number 3. You should recognize this as a sphere. Okay, it looks like a circle, but these dotted lines here give it some depth and you realize, oh, that's a sphere. However, be careful with this. This line is in through the middle here with the arrow pointing to it, they say is 16. That is the diameter. It goes all the way across through the center. I want half of that, remember. Radius is always half of diameter for circles and spheres. So I'm going to take 16 and divide by 2, and I get 8 centimeters. So my radius is 8. Now remember, for a sphere, the surface area of spheres is just 4 pi r squared. So my area or surface area is 4 pi r squared, which means I do 4 pi times 8 squared. Again, I'm going to do all my calculations separately, then multiply by pi. Or since I'm not adding and subtracting, this is actually pretty easy to just plug directly in your calculator. And I'm going to show you how to do that. Okay, that was 4 pi r squared. So I'm going to do 4 times pi times that 8 radius squared. I can put it in just like that, and I get about 804.2. I can even do it without the actual time signs. I can just do 4 pi 8 squared, just like I would write it on my paper without the dots for multiply, and it's going to give me the same thing if you're using this calculator app or a scientific or graphing calculator. So our final answer for surface area of this sphere is 804.2 square centimeters. Now, I forgot to classify it. I've been talking about it. I just forgot to write it in. This is a sphere, S-P-H-E-R-E. Okay, let's keep moving forward and try another problem or two. Okay, number 4 is a cone. I'm actually going to have you pause the video here and do this one yourself. I've already classified it. It's a cone, but I want you to do this. It's very much like the last one we did. It's just upside down. Now, pay attention to this fact. Same as last time, this is not your radius, this is your diameter. I want you to pause the video, try this one on your own, see what answers you get, and then I'll show you what you should have. All right, this is our answer we should get for the surface area of this cone. Since the radius is 5, when I plug in here to my surface area of a cone formula, I end up getting 81 pi, which simplifies or solves to 254.5 square yards. Okay? All right, for number 5, you should recognize this looks like this bowl shape is exactly half of a sphere. Half of a sphere is a hemisphere. Okay, so that surface area formula is, again, one you need to memorize. Surface area of a hemisphere is not the full 4 pi r squared, it's actually 3 pi r squared, because we have half of our 4, 2, plus an additional pi r squared on the top, so 3 pi r squared. So that's 3 pi times 5 squared, okay, or 3 pi times 25, which gives us 75 pi. When I do 75 pi, I get 235.6 square kilometers. Okay? All right, let's move right along to number 6. You'll recognize this is not a cone, not a sphere. This is a pyramid. The base of this pyramid has 6 sides, and they're all the same as each other. Otherwise, we probably couldn't do this problem, but they are the same. So the base of this is a regular hexagon. Okay? So we're going to classify this as a hexagonal or hexagonal pyramid. You can even abbreviate. Hexagonal pyramid. So to find the surface area, we're going to add up the individual flat surface areas. So the first one is the base, the regular hexagon. Remember, the area formula for a regular polygon is apothem times perimeter divided by 2. And we're going to add, the area of those triangles. All right. Now, each of these triangles has the same base, 6, because those are all congruent sides of that hexagon. So the base length of every triangle is 6. The height of each of these triangles, or the slant height of, the triangle height or the slanted height of this pyramid is 13.1, and all 6 triangles have that same slanted height. And so we can just do the area of one triangle and multiply it by 6. Okay, so we're going to do base times height divided by 2, and then we're going to multiply that by 6 because there's 6 of those triangles. So let's find the area of our regular hexagon first. Okay, first we need to know the perimeter of that base shape. Okay, perimeter is always the length of the side, 6, times how many sides there are. A hexagon has 6 sides. Okay, so the perimeter would be 36. Okay, the apothem is the distance from the center to the side of that polygon. So that's given to you as 5.2. So the area of this hexagon is 5.2 times 36, all divided by 2, because there's one of those bases. Then we've got 6 of these triangles. The base of each triangle is 6. The height of each triangle is 13.1. And divide that by 2. Okay? So when I simplify the area of the hexagon, 5.2 times 36 divided by 2, I get the area of the hexagon is 93.6. Then, whenever I get the area of one of those triangles, I'm going to leave my 6 outside there. One of those triangles has an area of 39.3 then. I did 6 times 13.1 divided by 2. And then when I do multiply that by all 6 triangles, I get the combined area of all 6 triangles is 235.8. Okay, so I'm going to add 235.8 to 93.6, and I get a total surface area of 329.4 square kilometers. Okay. All right, we're almost done here. The last thing we want to talk about is composite figures again, composite solids. And this is actually a little bit easier than what you might imagining at first, okay? So we are going to just basically add the individual surface areas. However, when you look at the individual figures, when you stick these together, some of the surfaces no longer exist as a surface because they're covered up. It's like they're glued together. They're not a surface anymore. You can't access them. They're inside the figure now. I don't include that. Okay, so the two shapes we're working with here first are a cone and a hemisphere, right? We're going to add a cone to a hemisphere. All right, so the area formula or surface area formula of a cone is pi r squared plus pi r L. The surface area of a hemisphere is 3 pi r squared. However, okay, for the cone, that base area of pi r squared is not going to be included. That base, that circle on the bottom of the cone is covered up. So all I'm really needing is this part. And for the hemisphere, I want to go back and show you this on the previous page. When we talked about hemispheres, okay? When we look right here, okay, that 2 pi r squared, it's the same as that one. That 2 pi r squared was half the area of a hemisphere, right? But this extra pi r squared that we add on to get 3 pi r squared isn't included when we cover it up with this cone. Okay, so instead of 3 pi r squared, it's kind of like we are subtracting a pi r squared from that to turn that into just 2 pi r squared. So all we're going to do for the surface area here is combine just that part, pi r times L, with just 2 pi r squared. Okay, rather than get a final and then subtracting 2 circles, I'm just going to not include those 2 circles. So the radius, again, is half of the diameter. That's the diameter. So the radius would be 8 divided by 2, which is 4. So my total surface area is going to be this amount, pi times that radius of 4, and then 12 is your slant height L, plus 2 pi r squared for the bottom portion of the hemisphere. 2 pi times radius of 4 squared. Again, when I'm using these surface areas for cones and spheres and cylinders, I want to do things in terms of pi. I want to do all my calculations except times pi first. 4 times 12 is 48, so that's 48 pi. And then 2 times pi times 4 squared, we got to do 4 squared first. 4 squared is 16. 16 times 2 is 32. And then when I add these together, 48 plus 32, I get 80 pi. Okay? So when we simplify this and get a final answer, 80 pi is about 251.3 square inches. Okay? All right, we've got one final example here. On number 8, these are the pieces that are put together. We have a cone on the left, so we have a left cone. In the middle, we have a cylinder, and then we have a right side cone. Okay, I'm going to use left and right to kind of help you distinguish between the two different cones. Now, again, the surface area formula for a cone is pi r squared plus pi r L. Same thing on the right side, pi r squared plus pi r L. The surface area of a cylinder is 2 pi r squared plus 2 pi r, not L this time because it's not a slanted height, it's a direct height between the circle bases. That's actually this length, left to right. That's our height measurement for that cone, so times h. But I want to show you what we're not including. If you'll notice, the circle base of the cones and the circle base of your cylinder are not included. These are being excluded. They're covered up. I don't want to include those in my surface area. So I'm going to take those out of the formula. For the left cone, that's the pi r squared. I'm not going to use that. I'm going to cross it off. For the cylinder in the middle, that's both of the pi r squareds. That's the 2 pi r squared part of that formula. And then for the right cone, it's the other pi r squared. Okay? So all I'm really adding are these pieces. Okay? The L for the left cone is 3. The H for the cylinder is 3. And the L for the right cone is 4. And the radius for all of them is 2. I've said all that. I want you to try and do that calculation now. I want you to pause the video here. I want you to do these on your own. Find a final answer, rounded to the nearest tenth, for the surface area of this composite figure. If you need more time, keep it paused. Otherwise, this is what you should get. A final answer of 81.7 square meters. Okay? If you have any questions about this, please send me a message. Otherwise, you should be ready to go on to the day 7.3 assignment.